Suppity sup, guys. So I just finished my first, or not my first, but my heat transfer semester, and I did pretty well. And so some of my classmates asked how I approached the problems, and so I thought creating a video of how I did my problems would help explain my approach to the problems and will give you guys a better understanding of how to approach them. I'm not saying my way is perfect, it works for me. Each will differ, so maybe you can use one of my tactics with yours to get a better grade. But to ensure that we're on the same level of understanding, I'm going to do these mini lectures beforehand. And so it's just going to cover a broad overview of what the chapter covers. So that way I can at least say we have a general understanding of how it does, or what I'm explaining. And so, but let me reiterate, these are mini lectures. These are probably more supplemental to what your teacher is teaching you. So you can watch it, yeah, sure, just so you understand that we're at least on the same teaching level. But you're not going to learn much more from this. Maybe it'll give you a better understanding of how something functions, but that's about it. Let me iterate. These are just supplemental, and this is more going to be problem focused. Okay, so let's get started. So to begin, there are three forms of heat transfer processes. Let me restart. I'm using Theo Bergman, Introduction to Heat Transfer, Edition 6, and Edition 5. And so the first chapter that they do is Chapter 1, which is just basically a broad view of the concepts you're going to cover. And so some of those concepts are like the three forms of the heat transfer processes, which is conduction, convection, and radiation. And conduction is the heat transfer across a medium when there's in the presence of a temperature gradient. Convection is the heat transfer between a surface and a moving fluid when they're at different temperatures. So when a surface of a material is exposed to air or water, are the two most common types of fluid. But when they're exposed to that, and usually it happens when the temperature of the air, which is represented by T infinity, which is temperature infinity, is less than the temperature of the surface, which is represented by Ts, which stands for temperature surface. And so that's when convection occurs. And so the next subject is radiation, which is definitely the harder of the two. I know conductions, I had trouble a little bit in the conduction of the chapter of conduction when you get into multiple dimensions. That gets a little harder. But radiation is definitely tougher. But radiation is the energy that is emitted by matter due to changes in electron configurations of its atoms, and everything's emitting radiation right now. So my skin is, your skin is, the table that your computer's on, those are everything's emitting radiation. And so I just want to go back to convection for a second. So a good example that most of us understand of convection is your CPU. So your CPU has that heat sink fan on it. That heat sink fan blows cold air onto your CPU to try and capture some of the heat, and so try and cool it down essentially. And so the way that it's built is also, it has like little fans, or at least mine does. So it's going to be like this big block that has individual layers in it. And so it's built that way for a reason. And so, which you'll see later in the chapters, that this design helps also add to the cooling process. So that is a good example, is your heat sinks. Maybe it's not called a heat sink, but your fan is in there, which is blows air on your CPU and on your components in there to help cool it down. Anyway, I digress. I'm going to cover these three subjects more in depth in the following. Alright, so let's get on to a little more in detail what each of these mean. And the formulas. More so focused on the formulas because that will help you do the problems. Alright, so conduction, as I previously stated, is the heat transfer across a medium. By medium, I mean like material. So like through a wall, that's a medium. If you have a frying pan, through the frying pan as a medium. That's what I mean by medium as material. But in this section, they introduce you to the concept of a heat flux, which a heat flux is the heat transfer in the x direction per unit area perpendicular to the heat flow, which is given by this formula right here, which is also equal to the heat transfer, or Fourier's law, divided by the area. So, and there's that dt over dx, which is the temperature gradient. And this formula also has a negative sign in it, which is just for proper uses, because a lot of the time you're going to subtract, when you subtract it, you're going to put the colder temperature right here, so something like that, you get negative 10. So to ensure that you keep your values positive, we multiply this by a negative, which will make it positive. So that's what the negative is there for. Then you're introduced to this little k right here, which is the thermal conductivity. It's material dependent, and it will vary with each material. And so, as you can tell, this equation right here is, well, to me, it looks similar to diffusion. That's kind of like what conduction is diffusion. So diffusion, I think, is the concentration over the time is equal to the is equal to the diffusion constant times the concentration with respect to the x direction. So they kind of look similar. This part does. I mean, I know this is the second differential, where this is the first, but they still kind of look similar. And that's you can kind of think of conduction as diffusion, because if you think about it, you're going to have a temperature gradient. So right here, you'll have this, we'll just say a wall, because a wall is a lot of what they use throughout the book, is because it's a very simple example. So you have a wall where one side of the surface is at TH, and the other one's at TC, and TH stands for temperature hot, and TC stands for temperature cold. Anyway, so again, there's a temperature gradient. So this temperature gradient, there will be heat being transferred. So you're going to have this higher heat going towards the colder side to kind of equilibrate it. So over time, it'll try and equilibrate. So you're going to start off like that and that and that. For, again, depending on the material, or depending on the constraints that are applied to it. And so it's going to try and equilibrate over time, where that instead of having this condition, oops, TC, you're going to have TH equal TC. That's if there's not a constant heat heat being applied to one of the sides of the surface. So, but even then, over time, this side will still try and equilibrate. Anyway, so if you can think of it as diffusion, so you can think of TC as the higher concentration, and it's going to diffuse to a lower concentration, which is TC. And so I think the book goes on and explains it the same way, where think of it as diffusion, and they talk about how the particles with TH will have a higher energy than TC, so when they diffuse to the TC side, the particles collide with each other, and so there's energy being transferred. So this one's going to have like very little velocity, and this one will have a high velocity, and so when they collide, it's going to transfer some of the energy to this smaller velocity one. So this one's going to have a little bit bigger one, and so that's kind of how they explain it in the book. So it is kind of like diffusion. Anyway, I digress. So they also talk about Fourier's law, which is essentially heat flux times the area. And so the units for heat flux are watts per meter squared, and the units for Fourier's law are watts, which are joules per second. And so, again, the formula is exactly the same, except the area is for Fourier's law. And so the way that the flow of conduction happens is it flows with decreasing temperature. So it will flow to the TC, the colder side of the plate or the surface. And so, but with today's views, they kind of think of it as lattice waves or phons. I haven't really taken a quantum mechanics class or solid state physics class, so I haven't really discussed phons too much. But phons are just lattice vibrations. And so, in non-conductors, the thermal conductivity is due to only lattice vibrations. And so, well, the heat transfer is only due to lattice vibrations, whereas in conductors, the heat transfer is due to lattice vibration plus motion of the free electrons. So, like metals, they had the CF of electrons, and so those add to the heat transfer, which gives it a higher value. That's why the heat transfer, well, even depending if the same constraints are applied, I'll say thermal conductivity. The thermal conductivity of non-conductors is much lower than that of metals, and that is due to this right here, so the lattice vibrations. So this is the way I think of it. So K for conductors, we'll put C is equal to the thermal conductivity of the lattice vibrations plus the thermal conductivity of the free electrons, the motion of the free electrons. Well, or for non-conductors, you only have the thermal conductivity due to lattice vibrations. And so that's the reason why that conductors transfer heat better than non-conductors. So I do these sections, or I do my videos in sections. So I'll do the general introduction, then I did conduction. Now I'm going to do convection. I can hear. I was listening to it, and you can hear J. Cole in there, and hopefully you're a J. Cole fan because I'm not going to go back and edit that. Anyway, so the next section is convection. Convection's heat transfer, the energy transfer, is due to random molecular movement, so kind of like conduction. And the bulk fluid motions. So what happens is when a surface is exposed to a fluid, such as the two most common types are air and water, the fluid carries away the heat. And so it carries, not that, it usually does. So the most common example is when the T infinity, which is the temperature of the air or the fluid, is less than the T of the surface. So this will happen. So then the fluid will carry away the heat. And so a major factor, or something that plays a major part in it, is the velocity boundary layer, and the velocity boundary layer causes the thermal boundary layer because of it. So this is fluid mechanics thoroughly. I learned all about the velocity boundary layer, or the hydrodynamic boundary layer in fluid mechanics. So hopefully you guys have taken that course. It makes heat transfer a lot easier. And so anyway, the velocity boundary layer happens when a free stream air, or free stream velocity of air or fluid, comes into contact with a plate or a surface. And what happens is that there's a condition called no slip at the wall, and essentially the molecules will stick. So the air, this is undisturbed air, or nothing's blocking this air, so that the fluid will come into contact with this and it will stick, and this sticking will cause the air velocity to be dampened, and this dampening, or the no slip at the wall, causes shear stress and viscous forces and shear stress. And so what happens is that when it gets stuck there, it causes a drag, and so the velocity here on the plate is dampened, so it's less than what the free stream velocity. When by free stream velocity, I mean it's when when the fluid is not blocked by anything, and so it will be dampened, and so the velocity is lowered, and so it creates this boundary layer, and the velocity will over time go back to the same velocity as the free stream velocity, but it will be dampened, and this right here causes the heat to be transferred, and so it also causes the thermal boundary layer, which is kind of like the inverse of the thermal boundary layers. But the heat is conducted into this layer, the velocity boundary layer, and is swept down and is eventually transferred to the fluids to the outside of the fluid of the boundary layer. And so convection can be classified as free convection, which is due to buoyancy forces and a density gradient, and forced convection, which is fans and pumps, and other stuff that you force air onto the surface of. So kind of like the fans in your computer right now and on your CPU, they cool down it, but they force the air in there. So that's forced convection. And so convection has its own heat flux. And so the heat flux for or equation for convection is this uh, Q double prime, which equals the heat or the convection heat transfer coefficient times the difference between the air temperature and the surface temperature. And this right here says I and F, which is infinity, but my program wouldn't let me write that. And so the main or a big difference between the equation is this, instead of between convection and conduction, is this heat or the convection heat transfer coefficient, which depends on the boundary layer, which are influenced by the surface geometry, the nature of the fluid motion, and the assortment of fluid thermodynamic and the transport properties. So you'll be introduced to something called a Nessel number, which you won't really need to cover right now, but that will give you a mathematical formula to show you what all the factors are. And so the convection heat transfer coefficient has units of watts, Kelvin, meter squared. And so the next topic we're going to cover is radiation. Okay, so one of the last topics and the more difficult of the three heat transfer processes is radiation. And radiation can be broken into two forms, which is emission and irradiation. And emission is radiation leaving from the surface to the surroundings. And so in emission, we have to, a lot of the time we compare our emission power to a thing called a black body, which is a physical body, and a black body is a perfect emitter. So it absorbs all the wavelength, and it's a diffuse emitter, and it's a perfect emitter. And so that's basically our standard that we compare it to. And the closest thing that we have to it is the sun. It's probably the closest thing to a black body that we have. And so we have to, we equate the emission power for a black body by this sigma times the temperature surface to the fourth power. And so this sigma is the Stefan-Boltzmann constant, which is the value for it is right there. But everyday items are not perfect emitters, so they're non-black bodies. And so to factor that in, we have to have this correction factor or scalar, I guess, for it, which is denoted by this epsilon, and is called emissivity. And it provides a measure at how efficient a surface emits energy relative to a black body. So as I said, we compare everything to a black body. It's like our standard. And so it ranges from 0 to 1. And so if it's 1, then it's a black body. But as I said, the closest thing that we have to a black body is the sun. And so it's essentially the same equation for a black body except the emissivity. And so the next not subject, but subcomponent of radiation is irradiation. And that is when radiation is being incident on the surface of the material. And so there are three outcomes of this. It can either be transmitted, which is usually by semi-transparent material. It can be reflected, which is usually by an opaque material. And what we're more focused on is absorption, or it can be absorbed by the surface. And that's more what we're focused on, because that plays a vital role in heat being transferred. Because if it goes through an object, it's not transferring heat really. And so that's why we focus more so on absorption. And so the absorption is denoted by this G right here. And so it's essentially, again, we would have the black body. And so we have to have a correction factor since it's not, since everyday items are not black bodies, and that's the absorptivity. So this is equal to the T Boltzmann constant to the surface time, instead of emissivity, it's alpha. And so the absorptivity which is again is denoted as alpha, depends on the nature of the irradiation, so the angle as well as the surface. So by angle, I mean the angle at which the light is hit, or the light hits the surface. And so again, it ranges from 0 to 1. And so there is a scenario in which in life that happens is called a gray surface, and that happens. What happens is the absorptivity and the emissivity are equal to each other, and so then you can get a net radiation. And so with the net radiation, you have to you add the emission, and then you subtract the absorption. And since the absorption and emissivity are equal, then you can just set one to equal to each other. And I previously stated that this right here is T surface for absorption, but it's T surrounding. Sorry about that. And so what happens is, I'll kind of break this out to you. Since those two are equal, so then you get epsilon sigma Ts to the fourth minus alpha T surroundings to the fourth. And so since those two are equal, you can just replace this with epsilon. So you can factor the epsilon and the sigma out. And so what you get is this. You get epsilon sigma times the temperature of the surface to the fourth minus the temperature of the surroundings to the fourth. And so they try and make the, then you can get the heat transfer for it. That's the heat flux. So this is equal to the heat flux. Heat flux. But then you can get the heat transfer of it if you multiply by the area. And to help simplify it, they use this little kind of heat convection, I guess, H, but it's which is represented by the epsilon alpha, which is the temperature surface plus the temperature surroundings times the temperature surface squared plus the temperature surroundings squared. And so then you, that's what the HR stands for the heat transfer. So then you get radiation. The heat transfer radiation is equal to this H sub R times the area times the change in the temperature of the surroundings and the surface to the surroundings. And so the Introduction to Heat Transfer book by Theodore Bergman teaches an approach called the control volume approach. And so basically, a control volume is a region of space bounded by a control surface through which matter or mass can pass. And so this can give us rate equations, which are very useful, and what I call energy balance equations. And basically, it's just adding all this stuff that's going into the control volume minus all the stuff that's going out of the control surface plus the energy that's generated, which gives you the energy that is stored for it, which is very useful. And so the rate of increase of thermal and mechanical energy stored in the control volume, so you get the rate, so we're going to do, which is, there are these equations right here, but I'm going to write it out for you. Stored in the control volume is equal to, must be equal to, the rate at which the thermomechanical energy enters the volume, so you get N minus the rate at which the thermomechanical energy leaves the control volume, so E out, plus the rate at which the thermomechanical energy is generated in the control volume. And by energy generated, so let's say you have this surface and there's a chemical reaction that goes on in there, and you call this material your control volume. So the chemical reaction that's going on inside, that's energy that's generated. Sometimes there might be a wire on the inside and it applies heat, and so that's another energy that's generated. Those are two scenarios in which energy can be generated. And so I probably should describe, again, this is fluid mechanics, this control volume approach. You learn a lot about this in fluid mechanics. mechanics. And so essentially what you do is you pick what you want to be the control volume, and you draw a dashed line around it. And there are like restrictions. You don't, for in certain reasons, you wouldn't pick certain areas. Like you wouldn't pick the whole thing. Sometimes it's just easier to do like a little differential volume of it, and then you can kind of integrate it over the whole entire thing. So that's kind of like the basic principles of it. Um, Anywho, so this right here gives us these equations right here. And so there's a condition in which uh, the what's coming in equals what's coming out, and that's called steady state. And so there's no change, essentially, there's no change in energy over time because what goes in is equals what's coming out plus the energy that's generated. And so that you actually use this condition a lot and when you're doing the problems, so that's why I mention it. And so you can also get the heat transfer. You can write it another way, which is the mass flow, which is m dot times the heat capacity times the temperature out of the control volume minus the temperature in. And so the mass flow rate is given by the density, the velocity, and the area of the object. And so sometimes there's also another scenario when you have to apply the control volume to just the surface of the material. So let's say you have this wall and you're only interested specifically in this wall, so you'll draw a dashed line, or this surface of this wall, so you'll draw a dashed line about it. And so there's no volume to this wall, even though there is volume. They say there's no volume to it. And so what happens, you have to add the things in and minus the stuff that's going out. So right here, you have conduction going into it, and you're going to have radiation leaving, and you're going to have convection leaving. So what happens is you'll get conduction, you'll get the heat flux for conduction, which is the N, which is En, minus the convection flux, and the radiation. And so that is E out, and this is when the steady state comes in, so it's equal to 0. And so that's a special case that you use sometimes, and I thought I probably should mention it.